Hello everyone, today we will be going over the blind 75 in C++, and today we're working on validate binary search tree. Now, before we get started, make sure that we already have our 4 questions already laid out to break down the problem. We need to ask ourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and what our output is going to be. So, to go over the question, given the root of a binary tree, determine if it is a valid binary search tree, where a valid binary search tree is defined as follows. The left subtree of a node contains only nodes with keys less than a node's key. The right subtree of a node contains only nodes with keys greater than the node's key, and both the left and right subtrees must also be binary search trees. So, to break down the following question, what does it mean by node's keys or node with keys? Well, keys is just another term for saying, hey, this is the value of the following subtree. So just by nature of binary search trees, nodes that are going to be less than the node's key or the node's value that we have with the current one, it's going to be on the left, and then greater is on the right. That's just based on principle. Binary search trees by principle. Left is less, right is more. That's just what they mean. And we just need to replicate this entire behavior and nature of the binary search tree just to determine if it's actually true. And it looks like we are just given the root of a binary tree. And then our output is that return true or false if we have a valid binary search tree or not. So, the technique that we will be doing for the following case is going to be recursion. We will create a helper function to determine the current node, the minimum allowed value, and the maximum allowed value. And to go over the steps of how we will replicate this, one, we're going to call upon a helper function we will create and then call upon throughout the rest of our solution is valid binary search tree with the root node and the minimum and maximum allowed values. Those are going to be some parameters we're going to create. And then step 2, we're going to create our helper recursive function that takes the current node, the minimum and max values. Then we're going to have a base case. If the current node is null, we're going to return true, and the reason being, and even in the case of an empty subtree, it is also considered true. Then we're going to check if the value of the current node is within the allowed range greater than the minimum and less than the maximum. If not, return false. Step 5, we're going to recursively check the left subtree by calling our helper function with the left child, the minimum allowed value, and the current node, which is set to be our maximum value. I'll just call it max value for short. Then we're going to do the same thing on the right side. Five. That's what we will do. First, we check on the right subtree by calling our helper function, and which is set to be our max. Right there. So we're just going to do the left and the right. And then finally, we're going to return the logical operators. We're going to return the logical and of the results obtained from checking the left and right subtrees, as well as the validity of the current node to see if it's actually our max value. So now to break down everything that we will do, just going to go out the steps. And since this will also be our output for our main type of function, we are going to have a helper function that's going to be called. So this is step 1. Return is valid binary search tree helper. We're going to have a root, our left, which we will set as null, and then our right, which will be default. And then we're going to create our helper function, which will be step 2. Private Boolean is valid binary search tree helper. We're going to have a tree node as a parameter, which will be the node for the root. Then we're going to have a tree node for our min node, and then tree node for our max node, because we know the relationship between them. Because anything that's going to be less is going to be on the left, right is going to be more. That's just the nature of binary search trees. Then we're going to have a base case that we're going to do. So that's going to be step 3, where if we don't have any node whatsoever, it's going to be a null pointer. Then we're going to return true in this case. Then we're going to check the value of the following range, which would be step 4. If, okay, min node and node value is less than or equal to the min node. Let me just correct that right here, val, or we'll do the same relationship for our max node. Node and node value is greater than our max node. Over here, we're going to return false, because we need to set up the entire behavior and relationship with left being less and then right being more at the same time, which is why we are doing this. Alright, I'm just going to put this right here. Check if the current node is within the allowed range, greater than minimum. So, this will be in the case where greater than the minimum. And then greater than minimum, less than maximum. That's what we do. Then what we will do with the data, we're going to do this for the left subtree, which will be if, and we're going to call upon our helper function, valid binary search tree helper, node, left, min, node, node. We're going to return false. Then we'll do the same for the right. Which will be our max node, and then max node. Hence, min node is on the left, max node is on the right. That is what we have. Yes, yes, yes. And then in any other case, we will have for step 7, return the logical and operator results of the right and left subtrees if everything's already checked out, and the validity of the current node, where all we have to do is just return true, because we already checked the following cases where everything is false. So by default, we will return true in this case. And I'm just going to make sure we have everything already right. If there are any syntax errors. Step 4. This is in the case where it is not valid, hence the exclamation mark that's already right there. All right, make sure you have this. All right, it passes all the test cases. Let me just clean all this stuff up for you folks. All right, submitting it. Okay, and to just give a breakdown and rundown on our space and time complexity for the following solution is that our time complexity for the following is going to be O of n, where n is referring to the number of nodes in the binary tree, and we visit each node at least once during our recursive traversal. And the space complexity is going to be O of n, since n also refers to the number of nodes in the binary tree. And we're using a recursion stack to be able to store everything that we have already visited for our nodes and then checking to see if it's true or false. Recursion typically would just be O of n by nature. And yeah, so this was validate a binary search tree in C++. Thanks again for taking time to watch this. If you found this helpful, like and subscribe. And if you have any other questions, please put them in the comment section. And as always, take care. Cheers. Bye-bye.